Hi, I'm Rex Black, President of RBCS. Welcome to the RBCS YouTube channel. Hey, I hope you enjoy all these free resources that are available here. And do us one favor. We need to keep the lights on and we need your help to do that. So, when you need testing and quality related services, training, consulting, expert services, you name it, let us be one of the bidders on that next job. We don't expect to get all of your business, but we'd like to get a chance. Thanks and enjoy the shows.
The broadcast is now starting. All attendees are in listen-only mode.
On behalf of RBCS, RBCS Australia, RBCS New Zealand, and Software TestWorks, we welcome everyone today to this webinar on advanced software testing with pairwise techniques. I'm Rex Black, President of RBCS, a worldwide testing and quality assurance firm serving clients ranging from small startups to Fortune 20 global enterprises. Since 1994, RBCS has been both a pioneer and leader in quality hardware and software testing. RBCS has offices in the United States, Australia, New Zealand, and Sri Lanka, with partners around the world. RBCS delivers insight and confidence to our clients, helping them get quality software and hardware products to market on time and with measurable return on investment. RBCS has a team of international consultants that deliver customized training, consulting, and outsourcing services for companies that are looking to improve their test and quality assurance practices. RBCS has helped hundreds of companies reduce development and support costs while assuring the best quality products are delivered to their customers. I am the author of Pragmatic Software Testing, Advanced Software Testing Volumes 1, 2, and very soon 3, Foundations of Software Testing, Critical Testing Processes, and Managing the Testing Process. I hold a degree in Computer Science and Engineering from UCLA. I am also past president of the International Software Testing Qualifications Board and the American Software Testing Qualifications Board. Before we start the presentation, a couple of housekeeping notes. If you have any questions during the course of the webinar, please feel free to submit them throughout the presentation at any time via your webinar interface. There's no need to ask for presentation copies. The presentation is available on the web at www.rbcs-us.com. There's also no need to ask how to register to win the free e-learning course. Simply by attending the webinar today, you have automatically registered to win. The lucky winner will be notified within 48 hours of the webinar, so check your email over the next couple days, and if you have a spam filter that things tend to get caught in, make sure you check that. We have a rule that if somebody doesn't respond within a certain period of time, 24 hours of being notified of being a winner, then we will select another winner. If you are having problems with the audio or visual components of this webinar, please contact GoToWebinar support. If for whatever reason you cannot get to the webinar online, or if you are dealing with an unreliable connection, please download the slides from the basic library at www.rbcs-us.com and be sure to use the telephone to connect rather than voice over IP. So with the preliminaries out of the way, I hope you enjoy this free webinar from RBCS. We do these free webinars as a service to the software testing community because at RBCS we're a not-just-for-profit company. Today's presentation is a continuing multi-part series on advanced software testing. We've done a few of these so far, and we've got a few more to come. Haven't decided how many we'll do. I'll know we're done when I feel that way, or when you tell me I'm done. The material comes from one of two books, either Advanced Software Testing Volume 1 or Pragmatic Software Testing. And today we are going to look at pairwise techniques of various sorts. Now, I chose to do this series of webinars on advanced software testing because there are many powerful test design techniques that have been developed over the last 30 to 40 years, but a lot of these techniques aren't in use. Why? Well, people aren't aware. of the technique, or they're aware of it but they don't know how to use it. They can't identify situations where they can use it, or they try to apply it and misapply it and give up trying to apply it. So this series of webinars is designed to help address those issues. So now, just to distinguish what we're talking about here from, you might be called unadvanced software testing, the basic techniques are things like equivalence partitioning and boundary value analysis, and to some extent the basic forms of exploratory testing and so forth. These are all straightforward and very useful for testing things like input field validation and proper alignment of reports and fonts and so forth. But if you really want to get into the internals of the system and what should or shouldn't happen, then you need to go beyond that. So we looked at a number of techniques: use cases, decision tables, state transition tables and diagrams. And those were useful for testing various kinds of business logic. Now, in this particular example here, pairwise techniques, this webinar, we're going to look at what happens when independent options might interact. So when I talk about independent options, I'm talking about we've got some set of factors, and each factor has various options that it could take on, like, for example, configuration options in a application, or various connection options that might be available. And those options can supposedly be set completely independent of each other, and either they don't interact or they interact in a very clearly defined way. So what we're looking for here is a way to test option interaction, or test for option interaction, without spending an inordinate amount of time testing every single possible combination. So, if you think we've got 10 options available for 5 different factors. It doesn't seem like a whole lot. You've got a screen, it's got 5 pull-down menus, and every pull-down menu has 10 different things you can select off of it. Like, well, how hard could it be to test that? Well, if you wanted to test every single possible combination, then you'd be looking at 10 to the 5th power, which is 100,000. And that's obviously not something that you're going to do. So we need a way to prune down the possible combinatorial explosion that could occur here, while at the same time giving ourselves reasonable confidence that we've tested enough, and enough, of course, in the context of testing is always a difficult word, but we've tested enough that we can feel that we've adequately mitigated the risk of combinational problems. And so the technique that we're going to look at to do that is referred to as pairwise testing. Now, again, what we're doing in pairwise testing is we're looking at unconstrained combinations of options for factors. So we identify various factors of interest. We identify the options that that factor could take on, the different settings that it could have. And we're going to make sure that we do 2 things. One is that we test every option at least once, but more importantly than that, every pair of options that could occur across all the different pairs of factors. We're going to test those at least once. And the way we're going to do that is we're going to create a tabular representation of factors with rows showing combinations of options for each factor. And then we are going to make sure that we test or have present in our tests, have covered in our tests, each row of that table. And by doing so, we can assure ourselves, as I said, that every pair of options across all the possible pairs of factors identified in the table have been tested at least once. All right, so what is the logic behind this? Why would we think that this would be, quote unquote, enough? Well, we know from the theory of equivalence partitioning that there are things that should be treated equivalently, and we want to make sure that we test those, and that's broad testing is covering of equivalence partitions, or a little bit more extensively the boundary values that exist. And the theory there is, that all these things are supposed to be handled the same way, right? So there's going to be a problem with any one of them. There's going to be a problem with all of them. And so by selecting a representative out of the equivalence class, or maybe two representatives at the edges, that if there's a problem with a particular option, then that's likely to come up. Now, what we're going to do here is we're going to build on that concept by saying, okay, yeah, there are definitely lots of problems that arise that way. There are also some problems that happen when two particular options are combined with each other. So they're fine by themselves, and thus equivalence partitioning and boundary value analysis would not get at the problem. But when you get them together, that specific combination of options together, then they misbehave in some way. They don't do what they should do, or they do what they shouldn't do, or they disable something else that's supposed to happen from happening. And this is concept of unwanted option interaction that occurs. Now, that's the hypothesis, that it's important to test the singletons, the representatives of the equivalence class, possibly by extension the boundary values of that class. And we're also going to try to test the pairs of the equivalence classes. But we're not going to worry about triples, and we're not going to worry about quadruples and quintuples and so on and so forth. We're not going to worry about higher order combinatorial tests because of the law of diminishing returns, basically, that the cost of covering those is disproportionately high. Empirically, the number of observed failures that are triple specific or quadruple specific, in other words, that rely on a very exquisitely precise combination of options, are fairly rare. And therefore we would spend a lot of money chasing after bugs in situations where we would be unlikely to find them. Now, I'm not going to get into the empirical data behind this. If you would like, there's plenty of documentation on orthogonal arrays and their use and why testing pairs is good enough out there on the internet that you can do further research on this. I'm going to basically take it as axiomatic at this point, take it as a given that this is the case, that going beyond pairs of options is going to be beyond the cost-benefit analysis, if you will, for testing, and therefore that this is something that's justified. Again, there is plenty of internet-based empirical material out there that you can look at, and if you're still kind of going, well, I don't know if I buy that, you try to convince yourself. And then, if in the alternative, if you cannot convince yourself, just run it through the practicality gauntlet and say, okay, well, suppose that bugs are just as likely to happen in triples as they are in pairs. Well, what's it going to cost me to cover all the triples? What's it going to cost me to cover all the quadruples? So I think both from a likelihood of finding problems and a cost to find problems approach, or a technique or analysis, it stands to reason that pairwise approaches make a lot of sense. Okay, so those of you who don't believe that at all, feel free to hang up now, because the rest of this is about how to actually implement pairwise testing on the assumption that you believe or accept that it is sufficient. And a gentleman in the session this afternoon who seemed very disturbed by this, and I think he needed to attend a different discussion about why it was sufficient. I see that nobody's dropped off, so you're all either convinced or willing to suspend your disbelief for the moment. Good. So there are two techniques that we can use to do pairwise testing. I'm going to explain one of them. I only need to explain the one because the other is self-explanatory, or at least the explanation is bundled with the tool. So one approach is what's referred to as an orthogonal array. And there's a big library of orthogonal arrays out here at this website. you'll notice that there's a really interesting and important phrase here, set of characters, ATT. So this is an AT&T website, and they are obviously very interested in combinations of settings because phone switches and other such phone network equipment has a lot of different settings in it. So they have a big library of orthogonal arrays that they put out there in I'd say the public domain. They're willing to share it with you at no charge. You just go out and download it. Now the question is how to download, which one to pick, and that is a question that we will answer shortly. Now another option, if you don't feel like going through the process that I'm about to explain to you, which is fairly simple, but does require a little bit of Googling around and screwing around looking for the right orthogonal array, is to go to this website here, pairwise.org, and there are a bunch of freeware and commercial all pairs tools out there, multiple freeware tools available. In fact, the National Institute of Science and Technology, I believe, in the United States, put out a very robust pairwise testing tool that in fact is almost the equivalent of a classification tree tool, which I might talk about a little bit later in another one of these webinars. It's a very sophisticated tool and it's available for free. I don't know if you're going to be able to find it at that website. You might. Try a web search for NIST pairwise software testing and see if that comes up with it. If anybody can find it, send me the link during this webinar. I'll be happy to push it out to all the attendees. Excuse me for just a second. No, thought I had a sneeze. Didn't have it. Okay, now, you can use either one of these approaches, orthogonal arrays or all pairs tables. Now, there are some subtle differences. I have never been in a situation where the difference mattered. I've had some people who told me that they thought the difference mattered, but those people were also involved in trying to sell a pairwise testing tool that generated orthogonal arrays, so I'm not sure I would consider those people unbiased sources. Anyway, there's the subtle difference is that the number of times that each pair of options is represented is equal in an orthogonal array and not necessarily equal in an all pairs table. The likelihood of that mattering, if you're using this for compatibility testing or for functional testing, as far as I can tell, is 0. So I wouldn't worry about it. Use whichever one you prefer. If you prefer to use a tool to completely automate it, do that. If you're comfortable with the orthogonal array technique I'm about to show you, then do that. Okay. We've all been dying of suspense. What's an orthogonal array? And here it is, an orthogonal array. Okay, now, an orthogonal array is a mathematical construct that has the property that every pair of options across every possible pair of factors is guaranteed to be represented in the orthogonal array. That's one of the essential mathematical properties of an orthogonal array. So if you're dealing with a true orthogonal array, it'll have that property. If you're dealing with a table that has a situation where there's a pair of options that you can identify across two factors and they're not in that table, it's not an orthogonal array. It's pretty much that simple. All right, so this is the simplest possible orthogonal array. Right here, doesn't get any simpler. We've got two factors. We've got factor 1 and factor 2. 1 and 2. Okay, now, each of those factors has two options, 0 and 1. Now, not only that, but every pair of options is represented in each row. Well, we've got 0, 0, 0, 1, 1, 0, 1, 1. Okay? Now, this particular situation is by no means amazing. You have 4 rows, right? And 2 times 2 is 4. Well, it's like no kidding, and there they all are, you know, and every possible pair is there. There's 4 rows, okay? Tell me something I didn't know, right? Nothing amazing happening yet, but now here's where it starts to get interesting. Get my highlighter up here again. Now, I got factor 1, I got factor 2, I got factor 3. Okay, so possible pairs of factors, 1 with 2, 1 with 3, and 2 with 3. So I got 3 possible pairs of factors. Okay, so let's go through each of the possible pairs of factors and satisfy ourselves that indeed every possible pair of options is present. Now again, we have 2 options per factor, 0 and 1. So we should find the same 4 combinations that we found on the previous slide, not necessarily in the exact same rows, but they should be there in some row. So let's start with 1 and 2. 0, 0, 0, 1, 1, 0, 1, 1. Cool. There it is. Now let's go with 1 and 3. 0, 0, 0, 1, 1, 0, 1, 1. Okay. And finally, 2 and 3. Oops. 0, 0, 0, 1, 1, 0, 1, 1. There they are. So they're all there. Now, some of you might be thinking, well, wait a minute. 2 times 2 times 2 is 8. So where are those other guys? Well, they're not there. We're not trying to cover all the triples, remember? We're trying to cover all the pairs. So we've covered exactly half of the triples. Which half? I don't know. I'm not trying to cover the triples. I'm not going to go through and generate all possible combinations, factors 1, 2, and 3 together. It's 1 and 2, 2 and 3, 1 and 3. Those are the ones I'm worried about. Notice that this has saved me a lot because I added this factor, 1 additional factor, but number of test configurations did not increase. Now again, what did I give up for that? I gave up for that complete coverage of combinations. I had that in the previous array. This one, I don't. But again, my bug hypothesis is that doesn't matter that much. My increase in risk is acceptable given the increase in cost that I'd have to pay to try to cover all the triples. In other words, in this case, twice as much. Okay, so what do you do with this thing? Okay, this has got some interesting mathematical properties, but it might not as yet be entirely clear as to what exactly this thing can do for me. Excuse me. I'm recovering from this cold. Let's suppose that we're testing a browser-based application, and then we go, you know, there's 3 factors that we're interested in. We're interested in the operating system, we're interested in the connection speed, and we're interested in the browser. And let's suppose that we're interested in 2 operating systems, Mac and Windows, 2 connection speeds, dial-up and broadband, and 2 browsers, Safari and Chrome. So when we would do this, if we say, okay, I'm going to have Windows every place I see a 0 here, and I'm going to have Mac every place I see a 1 here in the operating system column. And connection speed, I'm going to say dial up for every 0 and broadband for every 1, and then for browser I'm going to say Safari is the 0 and Chrome, the C here is the 1s. Okay, now I got Windows dial-up Safari, Windows broadband Chrome, Mac dial-up Chrome, and Mac broadband Safari. And I've tested every possible combination of operating system speed and browser, at least as identified here. So you notice that this is a real straightforward process. If you've got, say, Excel or some similar spreadsheet, you're just going to do a Control H to select a row, and then you're going to search and replace, replacing numbers with options. Okay, well that's fine, except that we have something of a problem here in that most of our configuration and compatibility tests aren't going to oblige us by fitting into this little tiny orthogonal array. We need something bigger. So we need to be able to select an arbitrary orthogonal array off of that AT&T website. So here's a simple, foolproof process for selecting an orthogonal array off of that website. Now, one is you identify the factors that you're interested in, whatever they are: operating system, browser, connection speed, the security software that you're using, any number of things, right? Whatever the factors of interest are. Now, the factors should be, of course, factors that have multiple options. If they don't have multiple options, they're not particularly interesting. They've got to have at least two possible options. And there should be some sort of mechanism by which the options could conceivably interact. You start testing combinations of things where it's just inconceivable that they could possibly interact. You're off into the weeds of testing. And just remember, everything that you test is something that you don't test. So you have to kind of be careful about this. Anyway, select the factors you're interested in, and then look at an orthogonal array and make sure it has at least as many columns as factors. And this makes sense from what I did on the orthogonal array on the previous slide, right? I replaced the headings on the columns with the actual names of the factors. Now, what happens if you find, hey, I can't find an orthogonal array that meets the other two qualifications on this slide, has that many columns, has too many columns, the one I find. Okay, well, that's cool because you can just drop extra columns. All the interaction goes on between pairs of cells on pairs of columns. So if you've got a column that doesn't correspond to any factor, then clearly there's no possible interaction there, so you can drop it. Now, you look in each column, the column is going to have unique numbers in it, usually starting at 0 and running up to 6, 7, 8, 9 potentially. So there have to be at least enough unique numbers in the columns to hold the options that you've identified for each factor. So if you've got 5 options for one of the factors, and yet there's a maximum of 3 or 4 numbers in the columns, forget it, it's not going to work. You're going to have to get a larger one. You got to get one that has enough numbers such that you can uniquely replace each number in the column with the name of the factor, or name of the option, excuse me, for that factor, and you won't run out of numbers before you run out of factors. Now, what sometimes happens is you identify an orthogonal array that's got too many numbers. Okay, no big deal. Once you've run out of the numbers, in other words, you've covered all the options that you need to, then the other quote-unquote spare numbers can be really done with any of the valid options. There's no restrictions here. It's tester's choice, as I say on this slide. Okay. Now, this last qualification is actually really unnecessary in the sense that if you meet the first 2 qualifications and you're looking at an actual orthogonal array, this third qualification, the third major bullet item here, will automatically be met. There will be at least as many rows as the product of the 2 largest number of options for the factors. So in other words, let's say you've got 4 factors. One has 2 options, one has 3 options, one has 4 options, and one has 5 options. Well, you would need to have an orthogonal array that had 4 columns, 5 numbers in each column. Usually there's the same number of numbers in each column, so it's 5 numbers in each column. And you would have to have 20 rows at least, though it would end up, if you had 5 numbers in each column, it would end up being 25 rows at least because of the fact that you now have 5 times 5. But you'd have to have at least 4 times 5, which was the number of options for the 2 factors that had the largest number of options. That sounds a lot more confusing than it works out to be in practice. In practice, it works out to be fairly simple. Now, one thing to warn you about, if there are too many rows, you can't just drop them like you can with the columns, because what will happen is oftentimes there will be interesting pairs or singletons in a row, interesting in the sense that they're not covered in any other row. So you have to check to see if that's the case before you drop any spare rows. Now, this isn't always something you have to worry about. I just mention it so that you don't go willy-nilly deleting rows without worrying about, am I cutting away something I actually need? Okay, I got a submarined. There it is. Okay. Mouse pointer disappeared underneath something or another, but now it's back. Okay, so you've located an orthogonal array on the AT&T website. You have downloaded that orthogonal array. You're ready to go. So here is a 5-step, pretty much infallible and almost entirely thought-free process for mapping your testing problem onto an orthogonal array. First, if there are any extra columns, drop them. So if you have 5 factors, you got 7 columns, drop columns. Which columns? Your choice. You can pick any 2 columns. I would recommend, though, that you pick the rightmost columns in the orthogonal array, because those are the ones that are going to be changing the quickest. Usually it's a good idea to keep the columns that change more slowly, and those are the columns on the left-hand side of the orthogonal array. This process, by the way, this mapping of the testing problem onto the orthogonal array, is going to be a lot easier if the first thing you do with the orthogonal array that you downloaded is import it into Excel or some other similar spreadsheet. Excel is particularly handy because it has a wizard. If you open a text file, that wizard will open up, and it will allow you to automatically divide the columns in the orthogonal array that you downloaded into columns in the spreadsheet, which makes your life a lot easier, which, after all, is a good thing, making your life easier. Okay, so you've deleted the extra columns. This is easy. Now, insert a row at the top of the spreadsheet into which you imported your orthogonal array, and write the name of the factor on the top, or factors, write the name of each factor at the top of each column, 1 factor per column. Okay? You can do this in any order you want, but usually you want the factors that are the hardest to change, those factors which have the options which take the most work to change, to be towards the left-hand side of the orthogonal array, because those are the ones that move the slowest. They change the least frequently. Okay? Again, entirely up to you where you put them, but that's my advice. Put the factors that are difficult to change on top of the columns that change the least frequently, which is usually on the left-hand side of the orthogonal array. Now, column by column, select the cells in the column underneath the factor heading which you added, and use the search and replace option, which in Excel is Control-H. Replace all the zeros with the first option. Place all the ones with the second option. All the twos with the third option, and so forth, until every option for the factor that you're looking at has been mapped onto a number. Now, at this point, you should run out of numbers exactly at the same time that you run out of options, or you run out of options before you run out of numbers. If you run out of numbers before you run out of options, you broke one of the rules on the previous slide, namely the rule having to do with the number of numbers in each column. Go back and get another orthogonal array that actually is consistent with the rules given in the previous slide. Now, at this point, you may very well be done. It's quite possible, but there might be some additional work that you have to do, especially if you were forced to select an orthogonal array that was particularly big. It might have some extra rows in it. So if there are rows that have a lot of numbers that were not replaced with options, then look and see. If you got a row that's all numbers and doesn't correspond to any of the options, it's completely extraneous. You can delete that one. If you have a row that has pairs in it, and you can convince yourself that those pairs of options for those particular factors are present somewhere else, then you can indeed delete that row. Or if there's partial overlap, you can figure out, in many cases, ways to combine rows together. The important thing is, remember, unique pairs or unique singletons have to be preserved. If you erase that distinction, then you lose the property that you're after here, which is making sure that you tested every possible pair. With step 4 done, if you need to do step 4, if there are any spare cells that were not replaced with options, then those can be filled in with easy tests, popular configurations, whatever. These are the tester's choice cells. Obviously, they have to take on some value. The value they take on is entirely up to you. Okay, let's consider an example. This is a real-world example. I'm doing compatibility testing of the RBCS-US.com website. Let's suppose that we want to do some compatibility testing. We want to look at connection speeds, dial-up, and broadband. We'll look at 4 operating systems: Mac, Linux, Windows XP, and Windows Vista. We want to look at 4 security options: operating system only, Symantec, Trend Micro, and McAfee. And we want to look at 3 browser options: Firefox, Internet Explorer, and Opera. Okay, so you see there are 4 factors there: connection speed, operating system, security, and browser. So we need 4 columns. Operating system and security each have 4 options, so therefore we need 4 numbers per column. And 4 times 4 is 16, so we would have to have at least 16 rows. All right, so here you see in the middle the orthogonal array that I found and downloaded off of the AT&T website, and here on the right-hand side, excuse me, get a drink of water here. Here you see the mapping of the testing problem shown on the previous slide onto this particular orthogonal array. So some of you are probably thinking, explain please how exactly this worked. Indeed, happy to do it. Okay, I got 1 column, 2 columns, 3 columns, 4 columns. So guess what? Column number 5, here we just delete, right? So we could delete it. Spare column. 0, 1, 2, 3. So we got 4 options. Right, 4 numbers there. 4 is the number of options for operating system and security. So that's cool. We got that handled. Okay. So I call this the speed column. All right. First, I insert a column, or excuse me, insert a row up at the top, and I put these names here: speed, OS, security, and browser up on the top of each column. See what happened there. First column, basically every place there's a 0, I put a DU. You can see here. Control H. Search and replace there, right? Or and then we got all the places where there's a 1. We've got the BB, broadband. 2 and 3 correspond to no particular option, so I replace those with a tilde, which indicates tester choice. Do what you want. Now, the next column, you see I got a 1 here, so the 1, that's a Mac. There's another 1 down here, and that's a Mac. Another 1, it's a Mac. And another 1, and that's also there. So it's just a matter of simply going through, search and replace, like I said. And if you're done there, you've got this nice looking orthogonal array here. And by the way, I misspoke there when I was talking about the operating system. I actually meant that the zeros got replaced by Mac. Making sure you guys were paying attention, and I'm sure you all were. Yes, the zeros are the Macs. Okay, so simple search and replace. I end up with this nice looking orthogonal array, as I said. Okay. So a few of these tilde things here, but these are all important combinations. None of them can actually be deleted. There's no place else where I have XP with Symantec, for example. Okay. So, very straightforward. Now, of course, with the Pairwise tool, it's even more straightforward than that. You're basically just going to download the tool. You're going to follow whatever directions come with the tool and explain how to use the tool and map the factors and options in that way, and then it's going to automatically generate the that pairwise table for you, and you're just going to go through and cover it with tests. So what we've got here in this webinar, the use of pairwise testing techniques to test supposedly independent options that might interact in some inappropriate way or constrain each other in some inappropriate way. So we're looking for interaction that we don't like. That's the whole point. Previous webinars like decision tables, state-based methods, use cases, we were looking at business logic, testing of business logic, and now we've added to that the ability of doing combinational testing in a manageable way, a way that we can explain to people and justify in terms of its manageability, as it were. So these advanced techniques are going to make you able to cover a wide range of problems now. You've got the ability to test with boundary values and equivalence partitioning for broad testing and for input values and those sort of things. And now you've got business logic tools with decision tables and state-based methods and use cases. And now you've got a combinational set of tools with orthogonal arrays and pairwise testing. So nice, broad set of testing tools available to you there to use in various situations. So that concludes the presentation proper. As always, I will put the advertisement up while I take questions. Happy to answer any questions that people might have. Again, submit your questions if you have not already via the question window in your handy GoToWebinar interface. A few questions via email came in. First question is one that has come up in the context of advanced techniques before, which is, would you expect people to use this and other advanced techniques exactly as described here? So as I've said previously on the other advanced techniques, yes, the examples are realistic and are immediately applicable. You can see that that was the case with the example that we worked through. It's a very common type of compatibility testing issue or problem with browser-based applications. Now, it's also true, though, that you have to think of these test design techniques as fundamentals, if you will. The analogy that I've used over and over again is that, you learn how to do things like play a musical instrument or play a sport by practicing fundamentals. So, if you're going to learn how to play tennis, for example, you're going to probably at some point, if you want to be really good at it, you're going to get one of those ball serving machines, and you're going to set that thing up to fire balls at you, and you're just going to practice your returns over and over and over and over again. If you're going to play soccer or football for people outside the United States, and you're going to practice kicking the ball over and over again into the goal, even though you're very seldom going to just be standing there in front of the goal going, kick the ball in. But of course, part of the point is to get in front of the goal and then know what to do with the ball when you have it. Similarly, playing scales on a musical instrument, you don't spend a lot of time playing scales on a musical instrument, but progressions of notes is definitely what it's all about. And if you don't know how to move from one note to another in a structured fashion with the musical instrument, it's you're going to sound like something out of a very, very, very bad punk rock song rather than a musician. So, you have to learn these fundamentals, and the same is true of these test design techniques, that you learn the fundamentals and then you apply them in creative ways. You basically synthesize test cases by combining the various test design techniques together to test what you want to test. Another question that, of course, would come up is, are these techniques exclusive of techniques like exploratory testing and white box testing? No, definitely not. Again, the point of knowing fundamentals, whatever those fundamentals are, whether they're black box fundamentals or white box fundamentals or experience-based fundamentals, the point of knowing those fundamentals is to be able to combine them together to attack the testing problem from a variety of different angles. And the more of these techniques you know, then the better off you are. It would be foolish to decide, well, this is the best technique in the world, and I'm just going to use this technique, because this would be like a carpenter who refused to use anything but a hammer because the hammer was his favorite tool. So you want to know how to blend these things together. You got to look for situations that call for one technique or the other, have enabling characteristics. Another question via email. You talked about code coverage in a webinar a while back. Do pairwise techniques relate to code coverage? No, they really shouldn't. In most cases, when you're using pairwise techniques, you're actually looking for situations where there's not supposed to be interaction, which means that there's not supposed to be interaction, then there's no code specific to that pair. Which would then mean that there really shouldn't be any code path that could be identified by any white box technique that you'd go down by testing the pair. So it's almost like anti-white box in the sense that you're looking for code that's not supposed to be there. If it does happen to be there, then you've found some way in which some set of a combination of conditions typically is not supposed to interact, but it is. So it's probably some sort of compound logic problem in an if statement somewhere, or race condition in terms of timing, or some other situation where there's an unforeseen code path of some kind. So no, don't go looking for code paths and a relationship between code paths and this pairwise technique. You're not likely to find it. Okay, well, seeing no further questions, I will close this session out. Let me tell you a little bit more about the resources available through RBCS. Now, we run these free webinar sessions about once a month, so please check our website, www.rbcs-us.com, to sign up. If you would like a special webinar presentation for your company only of this webinar or on any other topic related to software testing, please contact us at info@rbcs-us.com or via our website. If you don't already receive our regular free newsletter, sign up at rbcs-us.com. By signing up, you'll get valuable discounts on consulting and training services, along with a regular newsletter, which includes a featured article on software testing and quality and news about what RBCS and its partners are up to lately. You can follow us on Twitter at twitter.com/RBCS and also on Facebook at facebook.com/pages/RBCS-INC. Remember, check your email over the next day or so, including your spam filter, because you might be the lucky winner of a free e-learning course from RBCS. You were registered to win that for a random drawing simply by attending this free event. You can check out our digital library, which is on the rbcs-us.com resources tab. Look for the digital library that comes when you pull down that tab. And that has recordings of these webinars. It has podcasts, and it has videos, all of which are available for free. You can subscribe to our podcast via iTunes by entering RBCS Podcast into the search string. You can see videos and recorded webinars by subscribing to the RBCS channel on YouTube. We offer these free resources as a service to the software testing community, no charge, because at RBCS we are a not just for-profit company. That concludes the webinar. I would like to thank everyone for joining us today, and I hope to see you on upcoming webinars next month.